Hello, this is our ME165 project. Today we will be discussing how we will be improving a finishing sander. My name is Logan Olson.
My name is Aaron Francis Varma. And I'm Ethan No.
And this is our project. Our objective of this project is to recreate the design of a household appliance through SolidWorks and then apply stress analysis simulation through Ansys Workbench. And then we'd then potentially improve upon the design of the device. In this project, we will be doing a complete teardown of our sander. We will then be creating a SolidWorks assembly of our sander model. We will then apply FEA stress analysis on that model through Ansys, and then we will do the same for our improved assembly. For our chosen appliance, we will be doing it on a Makita 1/4 sheet finishing sander. The serial number and the model number are included on there. The purpose of our sander is to create a smooth finish on a surface. Typically, this is used on wood, but it also could be used on both plastic and metal. The sander mechanics function by having an armature powered by an electrical current, which then rotates elliptically, vibrating the sander pad. This creates smoother finishes on the surface. The armature also rotates a fan on the shaft, connected through the shaft of the armature, and it scoops up the sanded debris, which then gets sucked up and collected in the dust collection bag. An exploded view of the Makita sander could be found online through an e-replacement website where you could buy each part. On each component, a name is labeled for each part, so this will be used for our teardown. For a better look at each part, let's look at the teardown. On the top left is the left side of the housing set. Next to it, on the right side, is the fan guide where the fan would be placed on top of it. To the right of that is a housing set on the right side of the housing set rather. To the right of that is a set of tapping screws, which is there to encase the sander. Next to the tapping screws is the foot, which is placed directly on the sander pad on the right, which that then connects onto the housing set. To the right of that is a dust bag, which collects all the debris. On the bottom left corner is a field assembly, which supplies the voltage that is plugged into that, which then coils around the 115 volt armature to the right of that, which vibrates our sander. To the right of that is a series of M4 14 panhead screws, as well as a lever and clamper, which are placed on the sander pad. To the right of that is the sander fan, as well as a series of washers and other screws. Not mentioned on here is a few bearings that are attached onto the armature, as well as underneath the sander pad as well.
All right. This is our original design. We've decided to simplify the model a little bit, just to make it more practical on the time scale we were on, and also because a lot of the curvature was hard to model, especially for the case, making extruded supports and other such things quite difficult. So here you can see the case and the pad. There are slots for air ventilation, and on the next slide is our exploded view. Here we have all the parts we thought were necessary for good quality stress analysis. This includes the casing itself, multiple bearings, the armature, the fan housing, as well as feet supports and the sandpaper pad itself. And on the next slide, we have our FEA analysis on total deformation for the original design. Due to the challenges I've just mentioned, we were unable to get half of the case as there were some errors when importing it from SolidWorks to Ansys. But for the current deformation you see on the screen, there is a 900 Newton force coming from the bottom of the sandpaper pad and case, as well as the very top of the shaft is fixed. You can see the max deformation in the red corner closest to the viewer. And on the next slide, we have the equivalent von Mises stresses. The same force, 900 newtons, is applied on the bottom of the sandpaper pad. And you can see that the stresses are very low. There's only minimal stresses where the force is being applied near the center.
So for our improved design, we opted to go for a orbital sander as opposed to the finishing sander design that we had in the original. Here we have less components, which I'll show in the next slide. We also have a rechargeable battery, which allows us to remove the big cord that is attached to the original design. There is a round sander pad as opposed to a square sander pad. Again, it's orbital sander, so it makes sense for it to be round. And there is a switch at the top. So here's our exploded view. As you can see, our aluminum ion battery is the big square in the middle. There is a switch case, a power board, which connects the battery to the motor. There's a motor cover. There's a fan guide, a sander pad, and the housing, as you can see. So as for the motion analysis on our improved design, we wanted to analyze one of the holes that are at the bottom of the sander pad. So as you can see in the blue, that is our face that we chose to analyze. We added a 5,000 RPM counterclockwise rotation to the sander pad that goes about the motor shaft. And as you can see in the graphs, the angular displacement shows that that blue piece goes from negative 180 degrees all the way up to 180 degrees, and it oscillates through between those two degrees through time. As you can see, there is some noise in the graphs, so that would have to be due to the computers that we used. They weren't powerful enough to have the resolution that we wanted. You can see this also in the angular velocity. It's a bit choppy, even though it should be constant. It should have been a constant line. You could kind of see it in the angular acceleration a little bit, but it seems a little bit more of what we expected for a constant velocity, which would be a zero acceleration. Here is a video of it moving with the graphs. Okay. So here is our FEA on our improved design. First, we want to say that we chose the fixed support to be at the top where our hand would be placed. And the force being applied is like the original design where it's on the sander pad, and it's the same force. It's a force of 900 newtons. And here is our total deformation. So looking back at the design, there is a bit of a mistake that we made. The sander pad had walls on the edge of it, which were very thin, which is why you see a big red ring around the bottom of the sander pad. a lot of the stress happened there, and as you go towards the middle, it became more blue, as you could see. When looking at the von Mises stress, though, the whole thing is blue, which indicates that we have minimal stress as opposed to the von Mises of the original design, where there is a color gradient in the middle. This one has almost no color gradient. It is almost completely blue, which is better than the original design. And for our conclusion, we just want to conclude that our original design had some errors. One of the errors we could start with the lack of a mesh of half of the casing. It would be the left case on the original design. That is due to some faces having zero thickness, which messed with the assembly and with the transfer from SolidWorks to Ansys. Next, there was a lot of deformation on the improved designs sander pad. That is due to the very thin outer wall cover that we designed. A last error would be that while our improved design could be wireless per se, it doesn't mean that it's also cheaper. This improved design is more costly than the improved design due to that battery. So while you have more convenience, you also have to pay more for the improved design. But as for specifications that we fulfilled, again, it was more convenient. It had less components, so it was an easier build, and it had a simpler design as for how it works. And the rechargeable battery is a nice touch for if you want a portable sander. As for the analysis, the original design seemed to not have the best stress compared to the improved, but it did beat it in terms of the deformation. So that's the end of our presentation. Thank you.